Okay, so here we have the Rollercoaster Lab Practicum, and at point A, we figured out the gravitational potential energy at A, and we used a reference point at point B, and so that was 0.24 meters. That was our over here it says 0.26. Oh, right, okay. Because it's the height at point A minus the height at point B, so you get your change in height. And then we were able to figure out the velocity at B. Okay, well, wait, I'll come back to that. And then we did a flow diagram from A to point C. And at point A, now we're using a reference line at point C. So the change in height from A to C is this number, and we're able to get the amount of gravitational potential energy from point A using point C as a reference point. And then at point C, we were able to figure out the kinetic energy because we had the gate was at point C, and we know that the diameter of the ball is 0.01. We divided the diameter of the ball by the speed as it went through gate C, and we measured that speed using the tool that Mr. Day was using. It wasn't a motion sensor, or was it? I don't know. Anyway, and we got the speed at the gate, and so we were able to use that to solve our kinetic energy at point C. And then we go to point D, or from A to D, now we have our initial gravitational potential energy, and we can use our full height, and we get this number, and at each of the points we have E dis because there's change in heights, as you can see here, 50 centimeters to 24 centimeters, and then back up to 37.5 centimeters, and then back down 10 centimeters. We can't just take the initial amount of gravitational potential energy at point A and minus it from the gravitational potential energy at point D, because that wouldn't be accurate. So, but okay, that's what confuses me, because here, this is Hamid's board, but let me backtrack for a second, because from point A to C, we were able to get the amount of E dis because we have E dis coming out of our system, and we go Eg minus E dis is equal to Ek at point C. And so E dis is equal to the Eg minus the Ek. And Mr. Day told us to assume that half of the E dis from A to C is your E dis from A to B. And so we assumed that. So we were able to find our Ek at point B, and with that we got our velocity. And okay, so now let me explain the E dis part. Yeah, I was confused. So we got the Eg at point A using its full change in height from A to D. Then we got this, and we got okay. And then at point D, we measured the amount of seconds it took to pass through point D, and we divided that. We divided the diameter of the ball by the amount of time it took for it to pass through point D to get its velocity at point D. And then we calculated Ek, and we know our equation is Eg minus E dis is equal to Ek, so we're able to get E dis. during that time period. But see, that seems illogical to me, because you can't, I feel like you can't just take the EDIS that was calculated from point A to D, because there's all these changes in height. So I would think you would have to add the EDIS from A to B, and then add it again from B to C, and then add it from C to D. And I don't see a C to D flow diagram here. But anyway, maybe I'll ask you later, Mr. J. So we got to calculate the total percent of energy lost, we have our gravitational potential energy at point A minus the EDIS from point A to D that we calculated using our EK from point D, and all over the total gravitational potential energy from point A, and multiplying that times 100, and we get 56.4% of the total gravitational potential energy was lost. And there you go.